It's a randomized algorithm, but its running time is fixed. Right? There are n minus 2 iterations of this process. Once you pick an edge at random, which takes constant time, you have to contract the edge, which means you look at the adjacency list of these two vertices and put them together and do a bit of data structuring, but it basically takes linear time and the number of vertices. Because the adjacency list of the two vertices are total length at most n. Okay? And so you spend linear time. So it's n squared time overall. So this algorithm runs in n squared time. So the real question here, as I mentioned, is not so much how long does it take or whatever, is it correct? Does it even do the right thing? Yes?
Here we can add, right? With
Yeah.
two edges.
Yeah.
But if that vertex has more than 2 edges, so we'll conduct a complete set of
Yes.
edges, right?
Yes. Correct. But since at every step you always remove one vertex, you're constantly getting further and further down. Yes?
So why do you still need randoms? It's not
How many edges could there be in this graph? There could be n squared edges. A graph with n vertices can have n squared edges. All pairs could have an edge between them. Or something like that, right? It could be some n squared over 100. It could be some very large number of edges. I don't know exactly how many edges I'm contracting, but it's not that many.
So I want to say that contracting to 2 vertices.
Well, I'm contracting two vertices that have an edge between them. There are algorithms where you take two vertices that may not have an edge between them and contract them. That gets a little tricky. I'm not saying that. That could just destroy my min cut that way. I don't want to do that. Okay. So the question really is this correct or not? In other words, what is the probability that in this whole process, all the way to the end, I do not touch them?
Do not touch the what?
The min cut at all.
Is it n minus 1 by n?
Sorry?
N minus 1 by n minus 2.
N minus 1 over n minus 2 is probably not touching the min cut at all.
Sorry. Oh, you started on 1 by n minus 1.
Suppose it's a bipartite graph. Well, not bipartite. Suppose it's got two paths and there's edges crisscrossing. Well, actually, that's not a good case. That the min cut is of size 3, so or 2, 3, 2, yeah. But it's not. I mean, I'm not sure how you're thinking about it. It's not that simple.
But it's not this.
Yeah. Okay. So what we'd like to do is estimate the probability of picking it at an edge at random does not touch the min cut. And in order to do that, we need to build up some intuition about what's going on. So let's assume. Let me go to the next page. Let's assume that the min cut in the graph is equal to k. It turns out we don't actually need to know what k is, but let's just give it a name so we can refer to it. Oh, the value is k. Okay? If the min cut is equal to k, I claim that there are at least there are a large number of edges in this graph in terms of k. And here's the idea. Suppose the min cut is k. Can any vertex have degree less than k?
No.
If any vertex had degree less than k, that would be the min cut. You just cut off all the edges around it. So if the min cut is k, we know that the minimum degree of a vertex is greater than or equal to k. Okay, now there's this classic handshake problem. If you know the degrees of every vertex in a graph, do you know the number of edges in a graph? The total number of edges in a graph is twice the sum of all the degrees. Why is that? Because when I add up all the degrees of all the vertices, I count each edge twice. I counted one from one side and I counted once from the other side. So in other words, for any graph, this is just a basic property of graphs, the sum over all v in the graph of the degree of v is equal to twice the number of edges. Okay? So if the min degree is greater than or equal to k, that means all degrees are greater than or equal to k, then we can write this as 2e is greater than or equal to sum over all vertices in the graph k, which is equal to n times k. So the number of vertices e, which I'm going to call m from now on. Right?
What is that function?
Number of vertices.
Number of
So this I'm somehow implying this is a good thing. Why is this a good thing? Why should it be a good thing? The number of edges is very large compared to the size of the cut. Remember what I wanted to do? I wanted to pick an edge at random that was not part of the cut. Okay? Think of my set of edges as some kind of haystack, right? The cut is a bunch of needles and the edges of this haystack. If there is lots of hay and very few needles, if I close my eyes and pick something at random, will it be a needle? No, it'll be a piece of hay, which is a good thing. But if my whole collection of hay was all needles and I close my eyes and pick something in, I'm going to catch a needle, which is a bad thing for me. Because I don't want to pick needles when I contract. So saying the number of edges is large compared to the size of the cut is in some sense a good thing. Because now if I pick an edge with equal probability, what is the probability that I'm going to pick an edge of the cut? The number of edges is more than n times k over 2, right? So, so let's see. So, the probability of picking an edge of the min cut is, so probability that edge picked belongs to min cut is equal to k over m, because there are k needles in m in an m size haystack. But we just said that m is greater than or equal to n times k over 2.
Can you repeat how did you go from 2e to m? That was clear.
E is n. E is n.
E is m. Okay.
Sorry.
Okay.
The number, I don't want to keep writing the size of the set.
Oh, okay.
So the probability of picking an edge of the min cut from the entire graph is k over m, because we just said the min cuts of size k and there are m edges of the graph. But we just said that m is greater than or equal to n times k over 2. So this number is less than or equal to 2 over n, which you should think of as a small number. Because as n gets larger and larger, this number gets smaller and smaller. So see what I've done? I've used a basic structural property of the graph and a clever observation, a very clever observation by the way. This is not something you should think of as, oh, this is easy. This is very hard. That's why it took so long to come up with this observation in the first place. That somehow if you have a min cut of a certain size, the number of edges is reasonably large. It cannot be too small. It has to be reasonably large compared to the number of things in the min cut. So if I pick at random, the probability of hitting the min cut is going to be very small. Okay?
Can I ask a quick?
Yeah.
But as you pull out more hay, then your probability of getting a needle goes up, though.
Exactly. And that's where this thing gets really annoying. These are not independent. This works only for the first case. Right? For the first step, I can write this probability out. As things get more complicated, I can no longer write it this way, because you're right. In fact, the more success I have early on, the worse it's going to be for me later on, because there's just needles left. But if I do pick a needle, then I have to recalculate this whole, it gets very messy. So we're going to try and think about this inductively. Okay, we're going to say, okay, what is the probability of never picking an edge of the min cut if I have an n vertex graph? And let's call that P of n. Okay, so let's say that P of n is equal to the probability of never picking an edge of min cut in n vertex graph. Okay. Now I can write a recurrence. I know that P of n now is greater than or equal to, watch what I'm going to do here, 1 minus 2 over n times p of n minus. See what I just did here? What I'm saying is that I would like to express the probability of never picking an edge for an n vertex graph in terms of the probability for an n minus 1 vertex graph that I get after one contraction. After one contraction, the probability of not having touched an edge of the min cut is 1 minus that probability. It's at least 1 minus that probability because the probability of picking an edge of the min cut is at most that probability. So the probability of not picking it is 1 minus 2 over n. And now conditioned on the fact that I did not pick an edge of the min cut the first time, all I have to worry about is what happens later. And the subtle conditioning trick is another trick that we're sort of wrapping up under the recurrence, but can be made more explicit. If you want to see the analysis in the Kleinberg-Carter's book, they have it more explicitly written out. But in the notes, the Ericsson notes, then I think this is a bit cleaner. So we're saying that the probability of not making a mistake for an n-vertex graph relates to, first of all, not making a mistake in the first step, which is this probability, times the probability of not making a mistake after that, recursively. Okay? So recurrence is good not just for running time, but good for everything. And if you analyze this recurrence, and the way to do this, of course, is to unfold it. So you get something like, this becomes 1 minus 2 over n times 1 minus 2 over n minus 1. And if you, which is equal to n minus 2 over n times n minus 3 over n minus 1 times this telescopes out, you end up with something like 2 over n times n minus 1. You have to work it out, but basically cross terms telescope, but with 2 left over. So they cancel out. So the probability of success of this algorithm is a very, very minuscule 1 over n squared, which is really, really tiny, horrible. Yes?
Yes, actually, well, I have another way to get
Sorry?
this number. I have another way to get this number.
Another way to get this number?
Yes, actually, kind of much easier.
Good, do tell.
So it seems to me, well, why do you randomly pick edges? When you pick an edge, you're picking two nodes, two vertex.
Yeah.
Because other edges connecting to vertex are just collapsed.
Yeah.
It doesn't matter which edge you pick. So the point is that you are randomly considering pairs.
Yeah.
So just each pair is uniformly distributed.
Yeah.
So you just worry about the mean pair is.
But there are many pairs. If I have a min cut of size k, we don't know how many vertex pair witnesses there are. There could be one pair of witnesses with k edges between them. It could be k over 2 vertices with 1 edge between them. It could be many different things. We don't know the number of vertex pairs. That is harder to analyze.
The
number of edge pairs is easier.
That's choose 2 pairs. Right?
No, why? Why?
But
there are n choose no. There are n choose 2 pairs total in the graph of vertices. I agree.
Yeah.
But some of them are bad witnesses. Some of them are good witnesses. How are you going to conclude into that?
Is the mean kind unique? No.
No, it may not be.
Oh, okay. It's not.
Anyway, no, it's not. You could have more than one. You could have exponentially many. You could have exponentially many min cuts. It's an interesting thing about mine. So we have this algorithm which is terrible. It has a running time which is not great, but its probability of success is really small. No self-respecting algorithm should have probability of success that small. Because the n goes to infinity, the probability of success goes to 0. That can't be good. So on that cheerful note, we'll take a 2-minute break.
Can you explain the Pn? I did not understand how to do the Pn greater than 1 is.
So the probability of success with an n vertex graph. Success.
When you say success here, you
Never touching edge of the min.
and take note all this.
Well, you go you run the whole answer.
And the others have to go to all this.
Yeah, success is there. Okay? The probability of success there is the probability of making the first move correct. Then recursively having success there. Because one move plus
I was just going to say, it is going to be interesting how
the problem is the following. You could say, oh yeah, one pair must be good, so then you should So we stop here. You put on here. They have a whole bunch of different. If you've done this right, catch up. You put it on one side, on the side. Because if you pick two vertices, one side, one side, it's not easy. That's why we stop at 2. Yeah. For this one. Fine, we can oh yeah, observe one actually. It survived the first thing. I know that, but you have many chances to be back. Because when I start contracting, what does it start doing? Once a vertex absorbs a bunch of now your part of your has now been absorbed. As the job gets faster, the property of it is very good. I'm not saying you're wrong, I'm saying you're right. Again, I'm not saying you're yeah, exactly. Think so, we now have an algorithm for computing. We now have an algorithm for computing haircuts, and the probability of success, roughly, okay, 2 over n squared, or between friends. And as I said, this is terrible, but there's a way to make this not terrible really easily. Suppose, and this is a trick you're going to see over and over again in randomization. If I have an algorithm with a probability of success that's p, let's say I run it k times. Okay, so let me first back up a second. If it fails, will it give me a bigger answer than the correct answer or a smaller answer than the correct answer?
Bigger.
Bigger, because I'm not deleting, always contracting, right? Things can only go up. Okay. I'm going to run this 10 times and take the minimum of all the answers I get. What is the probability now that I have a bad answer? So think about it this way. I have a trial. Think of the algorithm as running a trial, right? And it gives me a number. I don't know if the number is right or wrong, right? But if the number is wrong, it's going to be above the. So if I take the min, right? When will I fail to get the min cut? I will fail to get the min cut if each of my 10 trials was wrong. If even one of them is correct, I'm done. Right? So if all of my trials fail, that means they all give me a number bigger than the min cut, then the min of them will still be bigger than the min cut. And I will fail. What is the probability of all of them failing at the same time if I run 10 trials? So the probability of failure with one trial, so the probability of failure is 1 minus 1 over n squared. It's a big number. What is the probability of 10? Sorry. That will be 1 minus 1 over n squared to the 10. Because each of them has to fail for me to fail. Not just one, they all have to fail. Now remember, 1 minus 1 over n squared is a number that's less than 1. If I take it to the 10th power, it becomes even less than 1. Which is good. In particular, if I run this, so if suppose I say what is the probability of n squared failures in a row? This would be 1 minus 1 over n squared to the n squared. And this is one simple trick you need to remember that we'll use all the time. This number, as n goes to infinity, is roughly e to the minus 1. E is Euler's constant. In other words, one second. I've gone down from a very large probability of failure, which is 1 minus 1 over n squared, in the limit that goes to 1. In the limit, my probability of failure is 1, down to a constant. By running this n squared times. It's not great, but I can get the probability of failure down to something small. And this will use this trick over and over again. Get a question?
Yeah, I thought the whole point of randomization was to reduce our running time. Now we're running at n squared times.
It's terrible, isn't it? What's the whole point of this? You're right. And we're going to fix that.
All right.
But this trick is going to be very useful. Once we have got the running time now down to a constant, then life becomes even better. What I want to say is that the probability of error is not just a constant. It's not like 10% probability of error. It's a probability that goes to 0 as my graph gets bigger. I want to be almost certain. So I'm going to make this number even smaller. Well, then here's a simple trick now. Suppose I run it. So run the algorithm. Some n squared times log n times. Okay? Now the probability of failure is going to be 1 minus 1 over n squared to the n squared log n, which is equal to e to the minus log n, which is equal to 1 over n. I brought my failure probability down from almost 1 to almost 0 by adding an extra log factor. And you can make this even smaller by just running it n squared times 2 log n, that makes n squared. N squared times 3 log n makes 1 over n cubed. You can make it really, really small. So to answer your question, what we want to design are randomized algorithms that fail with a constant probability. If you can get an algorithm that runs in this much time, that fails with this probability, then using logarithmically many more copies of it, which is still not very big compared to say n squared or n cubed, you can get the failure probability down to arbitrarily small. But if your original success probability was really tiny, then you're in bad shape already. Okay? So overall, this algorithm, if you want to get a failure probability of 1 over n, which is like a benchmark for good in randomized world, the running time of the algorithm is going to be, so the overall running time is going to be n to the 4th log n. Because each iteration takes n squared time, and you need n squared log n of these, and take the minimum log. And once again, I want to remind you, while in this particular case this has not been a very pleasing outcome, this idea that you can take an algorithm that fails with a certain probability and then repeat it again and again, and then take the combined answers in some clever way, to reduce the error probability is a trick we're going to be using over and over again. Yes.
What did we start with on the exhaustive search for the end of the fifth?
Yes. Or end of the fourth. If you're clever enough, it can be end of the fourth. So the exhaustive search strategy would actually be better than this. So we have not really done much yet. But like with any algorithm design, you start off with something that's kind of weak but is correct and gives you the basic idea, and you tweak it. I'm going to tweak this. It'll be a lot easier to explain the tweaked algorithm now that I give you the basic framework. Otherwise, the other one will just look like magic. So any questions about this analysis part? Again, the trick is to do repetitions, independent repetitions. And independence is important because I can now multiply. If you don't have independence, you can't multiply. So each time the algorithm runs, it chooses different random points. And what we've observed is that the key problem here in all of this, and the probability of success was really tiny. If you could somehow get the probability of success to be bigger, we'd be a lot happier. And in particular, what we know is that the probability of success is getting small because as you go further down the contraction phases, there's a higher and higher chance that you will destroy your algorithm by touching the midpoint. And that's what it means. You would like to do a lot more work kind of early on, when edges don't occur to you that much, and less work later. And so this is the intuition for the next algorithm, which came as a follow-up paper to this work that improved this a bit more. Okay? And here's the idea. So, let me see. So let's define sort of a series of contractions. So let's define a contract. G comma n over square root 2 plus 1 to be that okay? So do a few contractions. Don't do too many. So n over square root 2 plus 1 is like, think of it like, a constant fraction of the graph is still there. N over square root 2 is something like 0.7. So you do some contractions, but not too many. And just run it down. Okay? And so the new algorithm is going to do the following. It's going to contract the graph down a little bit. And that's one attempt to get a good contraction. It's going to do it again independently. And for each of these, it's going to recurse. So the algorithm will look something like this. So the algorithm, which again is in the notes, it looks like this. So the algorithm is A prime. It takes a graph and says, so if G is large enough, so G is not a small graph. Does that say more than, I don't know, 8 vertices or something? Right? Then call A prime on the contract of G comma n over square root 2 plus 1. And let's call the resulting value x1. And let's say x2 is equal to the recursive call of the same algorithm, doing it again, but with a different set of random choices. Yeah. Okay? And then take them in. Okay. So this algorithm is a bit more involved. It's saying, instead of just doing one contract operation all the way down to the bottom, which is what the original algorithm was doing, it says, contract a little bit. Okay? And then take this new graph and run it again. And this would of course make no sense, except that now we are doing this twice, independently, and taking the best one of each. So the top level, you're doing 2 contractions and doing it recursively, getting the best one. But at each level, you're doing the same thing again. Okay? So So again, we have running time analysis to do, we have correctness analysis to do, so we should look at what those two are. And let's think about now, let's first figure out what is the probability that the contract operation is safe. So we did the contract operation from n to n down to square root 2, right? N over square root 2. What is the probability that this operation does not touch any of the edges of the mean? Just doing up to this stage. We know if you do it all the way to the end, the probability of success is 1 over n squared. But we know in the beginning life is good. We don't touch edges of the min cut. So this should be a large number. What will it be? Well, you can do the calculation. Basically, it's going to be, as before, it's going to be the product of, n minus 2 over n times n minus 3 over n minus 1, all the way down to, what is it going to be? N over square root 2 plus 1, n over square root 2 minus 1. And again, if you do the gory details, this number turns out to be something like actually a very big number. If you think of 1 over n squared, which is a tiny number, this is a huge number. So, and that's, by the way, why we chose this weird parameter. You want to get some nice number. So the idea is that you run the contract algorithm as long as your probability of success is reasonably large. Okay? Namely half. So now we know something about the contract algorithm. So now we can figure out what is the overall probability of success of this algorithm. Now again, we use this following fact. If we repeat this algorithm twice and take the min, we only fail if both of them fail. Right?
But how do you calculate the minimum of exponential? Because you didn't.
The numbers, those are numbers. It's recursively, right? The output of the algorithm is the size of the min cut. So when you cause it recursively, it gives us the size of the min cut. The output of this routine is a number. So I'm saying get the numbers from recursive calls and take the min of the routine. Just like previously I said, run the algorithm n squared times, take the min of all the numbers, right? Okay, what is the probability of failure here? It's a probability that both of these fail. What is the probability that one of these fail? The probability that this algorithm fails is the probability that the contract operation fails, right? Or, and then recursively it fails after that. So, if we say that the probability is, let's say P of n is equal to the probability of success, okay? Then you can write P of n, and I'll write it first and explain what it says, is greater than or equal to 1 minus, because now I'm going to look at the probability of failure. The probability of failure is that both of the two steps fail. So that's something inside that with squared, because both of these things have to fail, right? And inside that, the probability of one of them failing is the probability 1 minus the probability that one of them succeeds. So it's 1 minus the probability of success. The probability of success is half, because the contract operation has to succeed with probability half, times P of n over square root 2. So again, this is how you write these recurrences. The probability of success is greater than or equal to 1 minus the probability of failure. The probability of failure is the probability that both of these fail. So it's some probability squared. The probability that one of them fails is 1 minus the probability that one of them succeeds. The probability succeeds is half for the contract times the probability that it recursive. So it all makes sense, but you have to keep doing these 1 minuses and multiplications over and over again to get this whole thing. And now we have a simple recurrence to solve, which is all in the notes, so I won't do it here. It's very complicated. But the answer is that this probability of success now, which you want to be much better than 1 over n squared, turns out to be and again you can prove. You can either back substitute in, or you can try to prove it directly, or you can do it. It's not that simple, because it's a kind of recurrence you've again never seen before. You have to unroll the whole thing and analyze it and do something clever. But now the probability of success, and you have to get used to thinking in reciprocals, right? Instead of being 1 over n squared, which is terrible, that made you run the algorithm n squared times to get some reasonable probability of success, is now 1 over log n. Which means if you now run this algorithm log n times, right? Your probability of success becomes a constant. And then you can run it log n more times, so you multiply those two, and you get it to be arbitrary large. So by the simple trick of observing that doing independent trials gives you a better chance of success, and then observing that in the beginning it's good to contract a lot, and then you get this probability. Again, this is a clever idea. You put these two together, and you get this thing. And now, of course, you can look at the running time of the algorithm. The running time of the algorithm is going to be something like T of n is equal to 2t n over square root 2 plus something like n squared, which will be roughly n squared log n. We have to run this algorithm log n times to get a constant probability of success. Then we have to run it log n more times to get a really large probability of success. So the new running time is something like n squared log cubed. And now we have an algorithm that actually runs faster than what we do.
The OS squared.
Because of the bookkeeping you have to do to sort of do the contraction. The contraction itself takes some time. Because you're running, roughly 0.3 times n contractions. Because n over root 2 is roughly 0.7 n. To get from n to 0.7 n, you run 0.3 times n steps. Each step takes n time, as we said. So it's n squared times for the contract operation. And there are two of them. So, yes.
Can I say something different on this?
As long as it's about randomized algorithms.
Yeah. Okay. So can we take another approach instead of doing the contraction?
Yes.
We just randomly remove an edge.
Yes. Remove it. You mean delete it?
Remove. Yeah.
Delete it.
Yeah.
Okay.
Between first only one. I want to decrease the degree of each vertex only by 1.
Okay.
I mean, for every two, just choose random 2 nodes and remove the edge.
Okay.
And see if the graph is parted or not.
Okay.
If the graph was not parted, then do another one and see. So we are trying to kind of reach the. There is a chance.
Okay,
of
but suppose the min cut is of size 5.
Yeah.
Suppose you're really lucky, you keep picking edges that are not in the min cut.
What?
Suppose you keep picking edges that are not in the min cut.
Yeah.
And the min cut's of size 5. You will run this operation m times. After each step, you'll run a max flow algorithm to check to see if, or you'll run a connectivity algorithm to check if your graph is disconnected. So it'll be m times n, so it'll be something n cubed.
So I mean, like if we kind of do the same thing with kind of randomly.
The problem,
separate-
by the way, there's a separate problem with what you're saying because the sequence of the deletions actually matters.
Yeah. For that, I think repeating the examination in separate experiments and then
Okay,
do the same.
in order to prove that is correct, you'd have to argue that out of the n squared factorial different ways of sequencing the edge deletions, with a high probability, many of them are good sequences. So you'd have to prove that. And that would allow you to conclude that your algorithm is correct. So I'm not saying you're wrong. This is what you need to show. You need to show that the probability of success over an n sequence, and there are n squared factorial of them, so you need a reasonably large number of them to be successful. One of them sort of works out nicely.
Yeah, well, I think we can kind of reduce the dat size, by something.
You may be, again, this is worthy of thinking about, but that's what you have to do to make it correct. Questions? So again, what I want you to take away from today is a couple of things. Perhaps the first thing is that, yes, there are algorithms that run with a guaranteed running time with a certain probability of error. And this is in fact, probably by far the most common kind of randomized algorithm you will see now in machine learning and data mining and even later on the track. Secondly, that when you have a certain probability of error, you can change it, you can reduce it by doing what is called amplification, by just rerunning your algorithm. This is expensive, but doesn't have to be so. It depends on what probability of error you start with. If you start with a decent probability of error, something that's not too large, like a constant, then with a logarithmic number of iterations, you can make it really good. And this is kind of mental shorthand that we use all the time. Just like with dividing and conquering, okay, you need things to be balanced and life is good. Here, you need your probability value to be roughly constant and life is good. Then with some log factors that we just ignore, that's another good thing to keep in mind. And also you need to keep in mind that just like before, what we're really studying, what we're really trying to do when we use randomization is find lots of good witnesses for things. In some sense, what we're doing here is saying, when we did that trick where we said, oh, if the main cut is the size k, the number of edges is at least n times k over 2, we're saying that we are able to show that there are many good witnesses of things to pick that will not hurt our algorithm. And that's an important observation of randomization. Like in the thing you just mentioned now, this example. The way you prove that a randomized algorithm succeeds is roughly by saying that if you think of the path the algorithm takes, right, has all these different paths leading to different outcomes. And if you mark each outcome as good outcome, bad outcome, good outcome, bad outcome, there should be many, many good outcomes. In a deterministic algorithm, all the outcomes have to be good. You can never make a mistake. In a randomized algorithm, you can make mistakes, but there should be only few bad outcomes. And you show that by saying the probability of a mistake. In other words, the number of bad outcomes divided by the total number of outcomes is roughly small. You do that by saying that I have many good ways to get to a solution. And every algorithm is different. There's no recipe for designing a randomized algorithm. But this is the surest sign that you might have some hope. That there are many good paths, and there are only a few bad paths. The few bad paths mess up your deterministic method, but the many good paths help your method. Okay? Next lecture, we will talk more about this amplification issue. Because it turns out that there are many more powerful tools for amplification that let you take a simple method and make it really efficient. And then we'll talk about more things. Right? So see you all.